Oh, alright. So let's continue this page. My recording stopped, so we'll finish off 15, 16, and then we can go on to page 3. So a car leaves Sun City and takes the road towards Mars City, which is 200 kilometers away from Sun City. Oh, wait. 14. I don't think I finished 14 on the other one. To determine whether something or not has a inverse function, some things are obvious. Like I said previously, inverse functions are when we can switch input and output values. If you look at C, obviously it is not you cannot have inverse functions because it has no input value. Notice it has no x. It's just f of x equals 3, a constant number, with no possibility for inputs. Therefore, since there's no inputs, I cannot switch input and output values. This one cannot have an inverse function. Now, there's also a technical definition for inverse functions. For there to be a possibility of inverse function, it is still switching input and output values, but it has to still be a function when we make the inverse. And so, for example, for f of x equals x squared, you can usually tell if you can have an inverse function. So we know f of x equals x squared is a parabola function. You cannot have an inverse if it does not pass the horizontal line test. Because if inputs switch with outputs, then if you have repeating output values, you're going to have repeating input values when you switch them in the inverse. So A technically cannot have an inverse. So basically you cannot have an inverse if it is not one-to-one. It has to be one-to-one for it to have an inverse. And parabolas are not one-to-one. They're actually many-to-one because you'll have many different x's going to the same y value. There are different ways if you can figure it out. We really quickly brushed through inverse functions, so if you don't remember this, that's fine. Don't stress about it too much. We'll hit it again one day when we review. Part D says, hey, part B says f of x equals 5x plus 1. We know this is a linear function. We know linear functions are one-to-one. They pass the linear line test, and the vertical line test. They'll also pass the horizontal line test, so they are one-to-one. So yes, these can have inverses. And then for the function f of x equals x squared, if I graph this function, square root x, you get this. And you can see, hey, this is one-to-one, which is great. And it does pass a horizontal line test. So this function is one-to-one, therefore it can have an inverse. Also, don't forget the answer keys here. So if you ever need to see worked out solutions, they're over here. It also has kind of more in-depth explanations of like, yes, it can be an inverse. No, it can't be an inverse. This is why it can't be an inverse. So don't forget those are there. So I have so many tabs. Here we go. 15 should look very similar. A car leaves Sun City and it takes the road towards Mars City, which is 200 kilometers away from Sun City. So we have a car that is leaving Sun City and going towards Mars City, and we have a distance of 200 kilometers. And then it moves at a constant speed of 70 kilometers per hour. So it has a rate of change of 70x. At the same time, a truck leaves Mars City on the same road, but in the opposite direction, so going from Mars City to Sun City. The truck moves at a constant speed of 60 kilometers per hour. So it still has a distance of 200, but it's moving at a different speed. So we have to find the equation for the car. But this was the one, we had it on the quiz, where we had to be careful. We had to say, okay, well, we have to find the equation of the distance from the car to Sun City. So we're measuring distance from Sun City in terms of time, x, in hours since the car left Sun City. Well, it's going from Sun City and it's going to Mars City. If we are measuring the distance of Sun City, we start at Sun City. So my starting point, my y-intercept, is 0. And we know my rate of change, which is 70. So we will have y equals 70x. Technically, it also should be c of x equals 70x, because they specify that you want to use c for the distance and x for hours, but either way is fine. For part B, it's slightly different because B is the truck and you want to measure the distance from the truck to Sun City in terms of time since the truck left Mars City. In this case, my starting point, we are not starting in Sun City. We are starting in Mars City. So my starting point in this case is we're starting 200 kilometers away. And as time goes on, I'm getting closer to Sun City. So my distance is shrinking. And they tell me I am moving at a constant rate of 60 kilometers per hour. So this is really difficult because you have to think through of how to set up the equation and what is your starting point and where you're going towards. And then once again, they kind of specify here that they want you to use t. So technically, this should be t of x equals 200 minus 60x. But once again, I don't want you to get too bogged down with technicalities. If you can at least write this equation, you're good. And then find how long it takes for the car and the truck to be at the same distance from Sun City. Find this distance. Once again, for this one, you can just use LinSolve or graph them and find the point of intersection. So let me go menu, algebra, not 1, 2. For LinSolve, I have 2 equations, and I'm going to have y equals 70x, and then y equals 200 minus 60x. And then this is my answer. They're fractions, they're decimal values, but that is my point of intersection. So 20 over 13 and 1400 over 13. You can convert them into decimals if you want. So for example, if you do 20 over 13, it'll be a decimal. If you do Control Enter, it takes you about 1.5 hours. And you can do the same thing for this one to figure out how much distance, at what distance they intersect. Part 16, the diagram shows the graph of the function f. I think that's f. So here is my function. Use the graph to answer the following questions. Find the value of f of 4 and find the value of f of inverse 4. So figure out what is y when f is 4 or when x is 4. So if we look here, when x is 4, y is 8. Now this one, this little tiny 1 always means inverse, so that means switch your input and output. So instead of my input being 4, I'm now going to consider my output as my input. Or my input's going to be my output. So with an output 4, what is the input? With an output 4, it seems to me that I have an input of, let's say 3. It really looks like 2.5. Because it's not perfectly on the line, but I'm just going to say input 3. So once again, this is inverse function, so you just switch your input and output. So instead of considering input 4, now it's considered your output 4, and then you see what x value you have for that output value. And then solve for f of equals -7. So this is a regular function, so solve for x when your output is -7. So when my output is -7, down here, my input is -7 as well. Oh wait, my input, when my output's -7, my input is -1. And then for this one, once again, it's a little bit tricky for inverse functions. So if it was a regular function without the inverse, it's saying, hey, find your input when your output is 1, but it's switched. So now it's saying, okay, find your output when your input's 1. So if my input's 1, right here, my output looks to be 0 because it's an intercept. And part C, write down the domain and range of the function of my inverse function. Notice here, it's probably easier to see on your paper. I guess I can zoom in. You do have endpoints. So it does not go on forever, which you can kind of tell because if it stops here, it does not go all the way down in your graph. So for your inverse function, your input and outputs are getting switched. So if you want to find the domain and range of the function for your inverse, you find the domain and range of your original function, and then for your inverse, the domain will be the range, and the range will be the domain. So first off, my domain for the original function, so f of x, my domain, it's continuous, so it's going to be an inequality. And they both have, or I don't see any open circles, so they're going to be equal to. My leftmost value is -1. My rightmost value is +4. My lowest value is -7. My highest value is 8. For the inverse function, you just switch them. So my domain is now my range. So -1 less than or equal to y, less than or equal to 4. And my range now becomes the domain of my inverse function. -7 less than or equal to x, less than or equal to 8. So because your input and output switches, your domain and range switches for inverse. And then draw the graph of f of, or the inverse of f of x. There's different ways you can do it. You can find the equation of the original one and then solve for the inverse function. You can figure out what values get switched around. So I'm going to switch around the values. That's how I'm going to solve it. So for example, the idea of inverse functions is that your x and y values get switched, or your input and output values get switched. So in this case, for example, this point would be 4, 8. Well, instead of having 4, 8, I'm now going to switch my input and output values, and I'm going to have a point that is 8, 4. And instead of having this endpoint be -1, -7, it is now going to get switched around and be -7, -1. And then just connect those points. This really only works for linear functions where you only really have to switch the endpoints. But notice it makes my domain and range true. Leftmost is -7, rightmost is 8, lowest is -1, highest is 4. So that's really easy a way. Just pick your endpoints and switch the x and y values. Numbers. Oh, this is the last page. How do I want to do this? I'm going to make it in a separate video because it looks like 17, 18, 19. It looks like the rest of them are arithmetic sequences. So on the video here.